All right, that come through the mic. Okay, great. All right, no, it was a great talk, and I think I can relate to a lot of these thoughts, and I'm going to talk about kind of from the large institutions resource planning perspective. So I've been spending time the last couple of years figuring out how you communicate the value of your research computing investment to all of your stakeholders, whether it's sponsors, university, or whatever else. Then that kind of begged the question is like, well, how do I know how much of these sorts of things I need? So I've got a few things I'll share around that. So previously on this show, if you guys have been here a couple years ago, I gave the long version of this that talked about putting a statistical model on measuring the relationship between the investment in cyber infrastructure to the outputs that your university cares about. Long story short, it basically boils down to with 20 years of data at Purdue, we can see that every 100 teraflops of capacity we invested in corresponded with an increase in $2.6 million of HERD expenditures. And similarly, basically every person we would fund in our research computing group corresponded with an increase in $12.5 million of research computing expenditures, which I think was a really nice output and a really nice outcome to find. You might ask the question, with a sample size of one, is that a reproducible result? Maybe, maybe not. All we need to do to be able to generalize that is get a bunch of institutions to provide 20 years of historical data and see if those models hold up. But I was able to get five. There were several very generous colleagues from around the country that were willing to share their records of their capacity and stuff over the years. And we were able to identify that the relationships are directionally similar across that whole data set and at the institutional level, and in some cases stronger. Like the research expenditures, for example, those same investments across that whole data set had larger returns than what we saw at Purdue. So, okay, this is good. We learned several other interesting things as we think about capacity planning for what you need at your university from this data set. We learned that our universities, as we track how much capacity we have over time, we had a compound annual growth rate in capacity of about 41%. It's almost Moore's law. Moore's law is the yellow curve there, and the actual is the black one there. So that was a good bit of thing to verify, and that made me think: could I use this curve to show to my administration that in 4 years I need to have X amount of compute? So when I did this, Purdue was an $800 million research expenditure place, and I knew how much capacity I had in 2022 and 2024. So I drew that curve. And it loosely tracks there kind of where I expect our planned refreshes are going to happen. So this has actually been really useful to go to my CFO, my VPR, and my CIO to say, hey, we're in a good spot right now. I guess this is 2026. So last year when I made this slide, we were in a great spot. Look, we're just above the curve where we need to be. But we're planning our 2026 deployment, which will hopefully get us back up above the curve. Now, the problem is Purdue's now $1 billion institution. So now the curve is up a little bit higher. But again, that'll help with that narrative with telling the university how much we need to invest. So again, more on how you know what is the right size of your campus cyber infrastructure. So if we talk to our researchers everywhere, some may want just a GPU or two, but the big, like our CS researchers, if I ask them how many GPUs they need, they basically say, I need all of the GPUs. Yeah, what my experience is that many of them say this, but then when you look at the actual usage data for what they do, it's much, much smaller. So we wanted to explore some of this a little bit. My not so hot take is that I think people who have done HPC for a long time, I think we have a good sense on like how we capacity planned our research computing investments in modeling and simulation, but it is not a fully baked science in the age of AI. So I set out a year or two ago to build out that data set that I wished I had earlier. So if I could build out that 20-year data set across how many institutions, we can really get some nice historical trends. So the first iteration of this survey, we've got, I think, about 30 institutions to reply with information about their staffing levels and the size of their computers. So it's not historical yet, so we can't run that full regression, but we were able to establish some really interesting relationships, and we can see that the average university in the data set had 8.7 petaflops of computing, spent almost $2 million on their research computing salary. And that is like what the institution's investing. That's not like chargeback. That's not grant funded, soft funded people on a team. That's like people who are in the IT budget or things like that. And then we can see that relationship between how much capacity you have as a function of your university's size. Like, for example, like UW-Madison, it stands to reason, would have better computing capacity than the small institution, in what a directional school, so to speak. I've used the same word. Michigan's going to need a lot more than Wright State. So okay, so we can make an estimate as to how much you need, either as a function of how many PhD students you're graduating, your earned doctorates, or the amount of research expenditures, and you can see those relationships here. We had a pretty wide set of respondents. We had a $2 billion institution and a $200 million institution, so a good range. So we can see some of the curves here, like what the model suggests that you would have based on your size in the orange, and then what people actually have. So it's an interesting way to get a sense. It's like, am I under-resourced or over-resourced, perhaps, as the amount of research that we do, or based on the number of graduates, PhD graduates that we award. Salaries, I think, will look to track a lot closer to what you would think based on the size of your institution. There's less egregious outliers there. Folks then came back after they provided data. They're like, hey, can you tell me like how many FTEs? Like, well, that's a great question. Well, if I have X teraflops, how many people do I need to run my center? So this has proved to be a really interesting data set. I've created almost a cottage industry of being able to, where my colleagues can ask me these questions when they're going to talk to their board of trustees or their CFO for their research for their resource requests. So I have the bright idea here. So if we've shown that there's a function, if your outputs are a function of your research computing investment, can you flip that equation around and make a rule of thumb about can we identify the system and people that we need based on the institute's production? So this is an example of what we could share with somebody, and this is Purdue as an example. In 2024, $840 million of expenditures and 810 earned doctorates, says we should have about 9.5 to 14 petaflops and 2.5 to 3.8 million dollars of people, and our actual numbers are somewhere right in the middle. So, between those two models is probably the reality of where a university needs to think of how much you need. So we've provided tables to other universities to kind of, your VPR can look up and see how big you are and get a sense on how many they need. This was shared with, I think there's a group of new VPRs in the AAU, perhaps APLU. I think it was APLU, and they actually loved this, and they love this information. A couple of them went to take this back to their institutions. So now, knowing how big you need in the aggregate, how do we design and capacity plan our deployments? And this is, I think, a hot topic with many of us who are building and deploying the machines. So our observations of usage patterns at Purdue, this is a screenshot from our XDMod reporting, looks like that. That's the job size on the x-axis, predominantly single GPU jobs. And I know nobody ever tells me that their job distribution looks different than that. So this is what our users look like. And the bottom there, that same picture, that is what the industry wants to sell us. It's like you're going to buy gigawatts of data centers in a super pod with a fully non-blocking interconnect so you can train a frontier model. So that doesn't seem like a good match. It makes me wonder, like, is it just us? Want to make sure that we don't have, am I a sample of one? I have the sense that it's not, because hallway conversations at workshops like this, it makes me think that we are, but I was able to get 12 Big Ten institutions to pool our Slurm logs effectively. So we have a 14 million job data sets across an entire year, 12 institutions and 21 clusters to see if these trends hold true. So naturally, this was really fascinating information. We can apply this in a couple different ways. First, work out, are we weird? If we don't need an expensive interconnect, can we all save a lot of money that way? Do we not need to get an expensive NVLink cluster node? Maybe we can use PCI GPUs to solve a lot of these problems. And what's the sweet spot for building a system? So the data set basically came out like this, seeing the job count in the GPU hours run on our systems. And it's overwhelmingly single GPU jobs. And you can see the mean job is 1.25 GPUs per job. The 95th percentile is 2. The wall hours are in 1.5 to 2 GPU hours. And 99% of the jobs are single node as well. So that first question about the non-blocking network, do I need to build a full SuperPod interconnect? Well, if you look at the data set, it looks to me like no. And even that, like half of those jobs that are multi-node, those are NCSA's Grace Hoppers. which have one GPU per node. So just if they want to go to two GPUs for a job, which is substantial, then that immediately becomes a multi-node job. So okay, I can save a lot of money on the network. We break that out by institution. Do they largely look the same? Yeah, they mostly do. You can see this is job count. You can see a couple spikes in a couple of spots. Ohio Supercomputer Center was one with a bump at 2, and it's 2 nodes, 2 GPUs on those compute nodes. So they kind of had a bump there. University of Washington is the weird one off there on the outside. They actually have a number of researchers that are doing model fine tuning on 8 GPU nodes. There is I think some interesting future work that we can do to figure out like what are the requirements of those? Do they just need the memory? Maybe they only need the memory to fit those things in there and they don't actually need 8 GPUs. So these new GPUs with lots and lots of memory may actually make this a little bit more efficient and drive the job sizes down by this metric. But GPU hours, of course, is probably a more relevant metric than just job count. So that does make a little bit more spikes once you start multiplying that out to 9 nodes times hours by GPUs times hours, but still largely holds true. So we came up with actually accidentally with a side effect of fresh data from that original survey, where we had the 29 institutions. We only had FP64 performance and not AI performance. So now we have a 12 institution data sets that looks like it's holding pretty true on the average FP64 per institution. And those relationships of the FP64 and the AI teraflops per unit of research expenditures or PhD has dropped a little bit for the FP64, but now we have a number that we can talk about on the AI side. So if your institutions ever wonder how much AI compute do we need, we have at least a starting point to make an educated guess. So I actually think GPU count is one of the key things for our researchers. I don't know if you guys all see the same sort of thing. That's more or less all they want is more GPUs with a certain amount of memory. Not necessarily pure performance, but also not too old and crappy. So it seems to me there's a Goldilocks zone in the middle where an institution should think about how many GPUs they need. So zooming out, we've all seen the Branscombe pyramid, right? We wanted to see if we could take these rules of thumb that we generated and apply it to the ecosystem scale. Could our national policymakers figure out how much compute we need in the institution? And this actually came out of a conversation with Amy Apon about some of these results. Naturally, I think NSF certainly would maybe be interested in knowing how much compute do we actually need. So we know that there was $108 billion of expenditures in the HERD survey. So that predicts that there would be, and at 11 petaflops per $1 million, that tells us that there should be about 1.2 exaflops of capacity that we need, that we have, and then that works out to be just 6.6 petaflops per R1. So our 187 R1s can deliver pretty much all of the capacity that the model suggests that we need for the entire nation, which I think kind of ties in well to that previous conversation. Thinking about small institutions without resources. If we know that in aggregate we have them, and the OS pool is a way that they can get to them, we have a really nice story to show that there actually is resources out there for people to consume. So now with 2 surveys, we can feel relatively confident in that number. So NSS capacity, this is kind of a wild guess, just based on the award sizes that we've had for MRI clusters and CC Star Compute Awards. I would guess that that's probably 0.1 to 0.15 exaflops of capacity. So that's a pretty narrow sliver of that 1.25 exaflops. Even the ACSS machines are less than an exaflop of less than 0.1 exaflops of that overall sliver of the pie. We do have the light tan though there. There's this interest in state level AI initiatives. So that's an unknown piece of that pie. How big that sliver is going to be will be interesting to observe and see how these state consortia start to evolve. So to wrap this up, interesting information. I want to tie this back to the audience here. So as I'm operating my campus cyber infrastructure, all I can think is the pendulum swinging back and forth from one end to the other. We used to run a very large condor pool at Purdue, harvesting our cycles. And I look around our campus today, and it's like we're back in the exact same spot we were, 15 years ago. I'm guessing that there's over 500 GPUs around our campus in workstations and do-it-yourself solutions that our researchers are consuming. That's only going to go up because we've got platforms like DGX Spark and DGX Station and RTX Spark and all these things coming out, all of which that are going to have a high-end GPU in them. Just ourselves, we're rolling out 150 plus DGX Sparks around campus, including we've got over 100 of them in a cluster right now. So I think I now have a desire to cycle harvest these. And yes, Marone makes the same gesture to me whenever I talk to him anymore too. He actually grabbed me yesterday. He's like, "Do you have those DGX Sparks up and running yet?" Yep. Uh-huh. So to tie it all together, we're here to talk HTC. We know that our hardware vendors are just wanting to sell AI factories, and they're going right to our states and our legislators and our university presidents and dangling gigawatt scale whatevers. I'm not going to write this down, but I feel like they're preying a little bit on FOMO because nobody wants to be left out on this. But like I said, I think the big metric for people is GPU count, not raw performance within reason. So the more reasonable GPUs that we can get the hands of our researchers, the better for what they want to do. And we always hear these tales in the news about the utilization rates at some of these commercial AI factories. They're not really very very upfront about it, but you hear very low, like 30% utilization numbers for some of these sorts of things. But our academic clusters are about 80% utilized. That's a good rule of thumb. So if you look at our Big 10 study, 7,600 GPUs among 12 institutions, with 20% of those maybe not being used. Again, we're back to 1,500 GPUs floating around the Big 10 that are ripe for the picking, right, Tim? And since these academic GPU workloads, they look very HTC because they're 1 GPU and 2 hours long. I think there's a real opportunity there. So action time. So for me, what we're considering, I was talking to some of my team even while I was here, is like, do I need to turn back on a several hundred GPU Condor pool? I know Tim is sitting here saying yes. And we're also looking at arrangements within our own state and region as to share these resources. So Purdue operates Anvil, which is one of the NSF access machines. We have some discretionary ability to allocate resources on that. Within our state more broadly, Jetstream is just down the road at our neighbors that we don't like to talk about. So our state is really in a pretty good situation resource-wise. The 2 NSF-funded resources, robust campus cyber infrastructure. So how can we make those resources available to our small peers in our state? Should Ball State and Indiana State and Marion College in the state of Indiana, we have the same problems that we heard about in Michigan. So we should have arrangements to give them access to these powerful machines. My finance people, of course, want to know how we're going to pay for this. So I would be happy to take their money, but I think we need to work out some of the financial challenges on that. We need to charge internal rates to academia, not try to do like a fully loaded industry rate because it's just it'll price everybody into doing the wrong thing. And then as a campus operator, we do have several spots where OSPool, I was actually troubleshooting with folks earlier this morning on our Anvil machine. How do we get more of our stuff into OSPool, make those resources available, put our money where our mouth is? And how do we push our PIs to the OSPool? The ones who always say, I'm out of GPUs. And like, well, it turns out we know people. We should make an effort to get them onto some of these national resources. So with that, that's the end of my slides. And I don't know if there's time for question or discussion, but happy to hear. Yeah, Stephen.
They're flying up. All right, I'll start with Pete, and then we'll go to.
Yep. My name is Peter Pismetti. I'm from Syracuse University. I'm curious if you could talk a little bit about some of the positive outcomes of your study and your model, positive in like how you've been able to use this to actually institute change or see others institute change based on these numbers.
So at my own institution, it's actually been really, really useful. If I have to rank the power of my executives at Purdue, the CFO is pretty much at the end of the day. he's the ultimate decider on lots of stuff. So if we need resources, we need investment, we need permission to spend, however $1 million that we were already planning on doing. If he's on board with it, he sees the ROI, this goes really easy. And the board of trustees as well. So we actually use some of this same data to get approval for a data center expansion. Purdue spent $16 million to, it's not the $100 million data center that I want, but it's a $16 million expansion to add cooling space to what we have already. And this information helps sell that to the trustees.
Quick follow-up, was that based on your internal numbers, or was that your executives looking at, oh, everyone else on this that is contributing more? Is this a competitive reason why they're deciding to invest more,
No.
or internal, like this is something I should be doing?
I don't think so. I think for internal messaging, the comparing to our peers, like the VPR and the provost, they care about that sort of stuff. But at the end of the day, the CFO, the CIO, and the board, like the bit about, if I invest this here, I get returns here. That's the only thing that they cared about. Like what other people were doing didn't figure into it.
Thank you, Preston. Stephen Deems at Internet2, formerly of a national supercomputing center. So I would say, yes, at our site, it was also predominantly single node, single GPU jobs for 98% plus jobs. And I just have a couple notes. I had so many as you were going. So that Washington blurb, I think you saw, that's probably the Allen Institute of AI out there doing the Olmo project. That's probably a group that really does need 8-way boxes, needs the interconnect. Your questions on, can you save money on the interconnect? Yes.
Yes.
Can you save money on NVLink? Yes. I didn't catch what your third one was, but it's probably
probably yes. Yeah. Turns out I knew the answers to most of these questions before I posed them.
I don't know if anybody responded to you from my old institution,
Yeah.
but there you go. Thank you.
Yeah.
Any other questions? Oh, go ahead, Erwin. On?
Hello. Erwin Laras from here, UW-Madison. Hey, I have a naive question. Why is teraflops the best unit to measure compute?
So we debated back and forth a little bit on what to use, because you could use total core count as one metric. That's kind of the other. And I still have people that advocate for number of slots as a good measure of scale. I think the challenge with that is it doesn't necessarily capture the capability of those slots effectively. So if I have 100,000 15-year-old compute slots versus my 50,000 AMD Milan compute slots, is my aggregate capability in my new stuff bigger? In most cases, probably it is. And then it also allowed us to sum up the GPU capacity in one single number. So those numbers in that first sample was like the sum of your GPU flops and your CPU flops all rolled into one.
Follow up. You mentioned that you have a Goldilocks, one GPU and a certain amount of memory, but you didn't say how much that was. So what is that Goldilocks space?
My experiences from what people tell us in Armon, if you know a hard number, feel free and correct me, but it feels like when people come to us, they say, I want a GPU with no less than 80 gigs of memory.
Yeah, that seems to be but there's definitely people who are like, oh, we need the H200, 100, da, da, da. But I feel like most people are happy with around 80 gigs.
Yeah, there's a couple of people.
But less than that, your mileage may vary.
Yep. Yeah.
Although we have generated a GPU eating machine in AlphaFold workflows. So
Yeah, so I actually wanted to ask, in terms of the GPU usage and looking at memory, are you looking at what the user is actually using in terms of their memory, or just what they're requesting?
I think we got what they requested. So basically what they told Slurm that they were doing. But of course, the other part was the question that was immediately begged. And I think what we probably see is across our institutions, we have varying degrees of instrumentation of how much we can actually tell that. Ours is we have spot checked some of that. A couple other institutions had some reliable data, but many of them don't even have that visibility into the efficiency of any of those.
The reason that sort of came up to mind was similarly when we started working with AlphaFold, everyone was like, I want a A100, I need 80 gigs of memory, so on and so forth. And quickly we realized most AlphaFold runs can run on like the smallest RTX you can find. And so as we started to open up that memory requirement, folks were able to run a lot more jobs. So I'm wondering what we can do in order to support that.
Yeah.
Smarter memory utilization.
Yeah.
Yeah, and I'd also be curious, just like how many people are doing inference versus training. How much are people like, have that data?
Yeah.
But that would be really interesting.
Well,
to
it
know.
stands to reason to me too that like even the people that I know are doing training, they're still showing up in those single GPU piles there. Yeah.
Just from lunch, but Chris Enderman, UW-Madison. I'm also curious about the memory usage because what I've seen from researchers is a lot of them are loading the same models into the GPU, right? And it's really inefficient. Like how many people are using AlphaFold? So we could maybe just host the models and then share those model endpoints. So I think that's a promising area of doing AI with HPC nowadays. Has Purdue thought about like a shared models as a service?
Oh, yeah. Do you want to answer that, Armand?
We have mainly seen that particularly in our Anvil GPU, Anvil GPT, and GenAI Studio services that we are hosting. There is one group of researchers. Researchers all need their own models. We started by hosting whatever researchers are requesting, but then now we are kind of getting to the point that, okay, what are the top 5 that we want to host so that we can effectively provide the maximum efficiency to people who are using those. So we are kind of moving towards that direction when it comes to AI applications.
Right. So do we have to move on? Yeah. All right. Thank you very much, Preston.
Oh, okay. It's
And
going to
then-
take a minute here. So if anyone's got anything else
Do you
quick.
have a final question, Rachel? Okay. Rachel is going to accost you at lunch, Preston.
Oh, okay. Ajit. Here.
Okay, this is Ajit Mahapatra, and I'm from UW-Madison Physics Department. So, any question for Preston? So, the GPUs that you have in your cluster, are those like all high-ends, A1, A, B, C, P1s, or mix of like others?
Yeah. Between all the clusters we have, we do have the alphabet soup, and I think we saw that across our whole data set across the Big Ten, because we have we have A10s, A30s, A40s, A100s, H100s, H200s, Grace Hoppers, and probably more.
So the thing is, because I'm actually asking it from the CMS point of view, because mostly they will probably, CMS does the training and inference. So they would, for us, for actually our students, whatever, we do actually flock to CHTC, but sometimes CHTC is totally booked. So in that case, I was hoping that if you could make your 800 into a OS pool or like make available a counter pool, maybe that will be useful. We can flock to Purdue and our students so I can use it.
Another vote for the 700.
That will, yeah,
GPU pool.
they will appreciate it. Thanks.